Hey everyone, and welcome to this explainer. Today, we're going on a seriously fascinating journey unpacking the literal architecture of our planet. We'll be starting huge, mapping out the massive macro habitats of the natural world, before zooming way down into the physical engineering of the animals that live there. And finally, we'll explore how we as humans actually take Earth's raw elements and micro-engineer the modern world around us. So let's jump right in. Okay, to kick things off, I want you to consider this for a second. What do a shark skeleton, a delicate little spider web, and the massive steel arches of the Eiffel Tower all have in common? I know, right? It sounds like the setup to a weird joke. But I promise you, there's this incredible narrative thread that connects the biological engineering of the natural world directly to our own human structural engineering. Here's our roadmap for today. First up, the web of life. Then, skeletons and natural structures. Third, the cycle of life. Fourth, metals and nonmetals. And finally, number 5, processing our natural world. Okay, let's dive into this with section 1, the web of life. So the absolute foundation of this entire web is biodiversity. And really, that's just a fancy word for all the living things found in a specific habitat. Take a place like South Africa, for example. The sheer variety of habitats there is, well, it's staggering. You've got wetlands, bushveld, grasslands, deserts, forests, and oceans. And every single one of these habitats is absolutely teeming with indigenous species. Plants and animals that naturally occur right there and nowhere else. And the wildest part? They're all completely interdependent on one another just to survive. Now, usually when we talk about South Africa's wildlife, almost everyone immediately thinks of the famous Big Five mammals, right? Things like the lion, the elephant, the rhino. But nature loves a good surprise. Beyond those mammals, South Africa's unique biodiversity actually boasts what's known as the Big Six birds. We're talking the Kori bustard, the hornbill, the Marshall eagle, the saddle-billed stork, the Pell's fishing owl, and the lappet-faced vulture. These magnificent indigenous birds are super vital to their interconnected habitats, soaring high above to find food while relying completely on the earth below for their shelter. But, as you might guess, there are incredibly high stakes here. This beautiful, delicate balance is under serious threat. As human populations expand, we're literally destroying natural areas just to make room for our own housing and food. And on top of that, we're polluting the earth. When you disturb the delicate balance of a habitat like that, these incredible indigenous species become threatened, or worse, face total extinction. I mean, right now, species ranging from the tiny, hardworking honeybee all the way up to the massive white rhino are at serious risk. To really understand why losing even just a single species is such a big deal, think of the food chain like a dynamic, high-stakes production line. You have producers, green plants that capture solar energy to literally manufacture their own food through photosynthesis. Then come the herbivores, the consumers that process and eat those plants. And finally, the carnivores, which hunt and eat the meat. If you wipe out any single stage of this processing line, the entire ecosystem's engine just completely stalls out. Section 2, skeletons and natural structures. Now, what's really interesting about this is how nature solves the whole problem of structural support, and it does so in 2 completely different ways. On one hand, you have exoskeletons. These are the hard outer shells you see on invertebrates, like spiders, scorpions, or crabs. And sure, they provide amazing waterproof protection, but there's a pretty big catch. They limit growth. To get any bigger, the animal literally has to shed its own skeleton. On the other hand, we have endoskeletons. Vertebrates, like us humans or frogs or elephants, have internal bones that are covered with muscles. And the really brilliant part, our endoskeletons actually grow right along with us. Plus, an animal's skeleton completely dictates exactly how it moves through the world. I mean, just look at how perfectly engineered these adaptations are. Flying birds have these large, hollow skeletons to keep them super light so they can actually soar on the wind. Frogs, they rock webbed toes and crazy strong hind legs, making them absolute dual threats for hopping on land and swimming in water. Snakes just completely ditched limbs altogether. They use incredibly strong muscles pushing against the ground to slither around. And fish, or even massive sharks, have skeletons made largely of cartilage. It's this tough, highly flexible substance that lets them effortlessly whip their tails side to side through the water. And hey, this is actually where we answer our opening question. You see, nature relies heavily on frame structures. Those are parts joined together to support a load from the inside. A delicate spider web, a complex beehive, and the endoskeleton of that frog we just talked about, those are all natural frame structures. So when humans started building and engineering, we essentially just borrowed that exact same blueprint. The Eiffel Tower, the frame of your bicycle, those giant power pylons you see on the highway, they are all man-made frame structures. We're literally just mimicking the biological engineering that nature perfected millions of years ago.
Section 3, the cycle of life.
Let's shift gears a bit and look at the slow, super deliberate structural engineering of a plant. It all begins in phase 1 as a tiny, simple seed. Once it finally gets some water, the plant literally breaks open its shell. In phase 2, it germinates and starts to grow. By phase 3, it becomes a seedling. And honestly, this is where the real engineering happens. It sends a taproot shooting straight down deep into the soil to anchor itself and hunt for water, all while the stem pushes aggressively upward to support the plant against gravity. It's essentially building its own foundation from scratch. And animals engineer their own life cycles quite differently too. Mammals, for instance, rely on internal fertilization. They painstakingly protect just a few young safely inside the mother's body, nourishing them through an umbilical cord. It's a huge investment of energy. Meanwhile, species like frogs and fish, they go a totally different route. They rely on external fertilization, essentially playing a massive numbers game by laying and fertilizing thousands of eggs out in the open water. Section 4. Metals and nonmetals. Now zooming out to the raw materials themselves, the Earth gives us two incredibly different types of building blocks. First, metals. Think iron, gold, silver, aluminum. These guys are shiny, they're hard, strong, and they're malleable and ductile, which is just a fancy way of saying we can bend them or stretch them into thin wires. Plus, they're amazing conductors of both heat and electricity. On the flip side, we have nonmetals, like wood, plastic, glass, or rubber. These tend to be pretty dull on the surface, they're poor conductors, and a lot of them are brittle, meaning they'll just shatter or break if you hit them hard enough. So the crucial point here is that we humans didn't just settle for these raw elements as they were. No, we learned how to mix them. An alloy is simply a mixture of metals. By mixing iron and a bit of carbon, we get steel. By mixing copper and tin, we get bronze. We literally take these base elements and combine them to engineer totally new, superior materials that are stronger, harder, and critically, highly resistant to rust. And that, my friends, is exactly how we're able to build our most incredible machines. Bringing us to Section 5, processing our natural world. Just like a green plant processes sunlight to make its food, we process raw substances to meet our own massive society-wide needs. But why do we actually go through all the immense trouble of mixing, heating, cooling, and firing these materials? Well, we process them to make our products far more durable, to manufacture affordable goods on a massive scale, to make our food taste better, and ultimately, just to develop the huge variety of useful items that keep our modern world running smoothly. And this brilliantly illustrates the real-world results of all that work. By processing the earth, we create concrete, which is intensely strong, watertight, and fireproof, perfect for building giant bridges and dam walls. We take ordinary sand and process it into glass, giving us waterproof, transparent windows. We create highly versatile, economical plastics for all our tools and pipes. We even process gypsum to create fire-resistant ceilings. And, get this, the hard splints that doctors use to fix our very own broken endoskeletons. We essentially take the raw earth and we re-engineer it into the protective shells and frame structures of our everyday lives. We've really journeyed quite a bit today, from the fragile, intricate web of a spider all the way up to the immense, towering steel of the Eiffel Tower. As a species, we are incredible structural engineers, mimicking nature and processing the raw earth to build these wildly impressive human habitats. But I want to leave you with this final, provocative thought. We've completely mastered processing the earth to build our own structures, but are we really doing enough to protect the natural biological structures that sustain us? Our engineering is undeniably brilliant, but without the rich biodiversity of the natural world, our own habitat simply cannot survive. Thank you so much for joining me on this explainer today, and I really hope it changed the way you look at the architecture of our amazing planet.